Great, thanks for having me. I want to basically talk about the need for grid integrated buildings. I'm going to focus more on kind of commercial stuff and really try to show that there is a way here and that we can do all this. So really, I'm going to kind of just, the big crux of, I think, the problem here is we're either going to be having to upgrade this massive grid, or we've got to figure out how to fit it all. So that's kind of the basis of what I want to present. I'm making the argument that decarb plus efficiency is absolutely crucial, and I'll kind of go through case studies to kind of make this point. So here we go. So again, a little background primer on Ecotope. Ecotope is basically a research and a design firm. We have, in our design work, we focus on three main kind of key concepts. One is obviously electrify everything, everyone's there. Another one is called design for off. This is something that we've been practicing for about 12 years now. And then a third that's sort of emerging is when matters. And so when matters means when you use the energy is going to be more important than how much you use. And we're starting to see this now with the grid congestion. Next. Again, this just kind of reiterates what I had said before, but electrify is kind of a key theme. That's all we do. We don't do gas design, so we've been doing it for about 25 years. We've done quite a mix of projects, so I want to show some of that to you. Design for off is essentially a strategy that you try to implement and turn stuff off deliberately as an approach to energy efficiency. It works great if you can get it all kind of tuned up, and I'll show you some examples of that. And then when matters is just really focused on trying to change the load shapes of our designs. So not just shift, but actually selling load shape and selling a different one. And that's what we're trying to do, is try to develop and bring to scale different load shapes. And that is kind of a key agenda. Move forward, please. Okay. So again, this just kind of reiterating, we're either going to spend a lot making this, making the wires fatter and kind of, bringing everything up to kind of handle all of this peak and all of this problem, or we've got to figure out, how to kind of stretch it along what we've got. And we have to be doing that way because this way is going to be awfully expensive. Next. We do have to kind of learn from the past. I want to bring up a project. This is kind of the foundation of Ecotope. It's a project in Washington State called Whoops 2, and this was, ironically, and it was two big nuclear plants that were going to basically come in and save the region on all this growth. And the founder of Ecotope, Dave Balon, stormed the Bonneville meeting in '83 and said, if we insulate all the attics to R11, remember this was before energy codes, we have the same energy as your nuke plant. And that started conservation. So that's a really important thing. I feel like what we're about to embark on, trying to kind of fit all this electrification into the grid, we have to learn from our past here, because conservation, there's a lot of fat still in all our buildings, all our grid, the NEC, and all of our electric in these buildings. So it's pretty crucial to really sort of look at that and figure out how we can do this decarb work without any transformer upgrades. So that's kind of the criteria, is let's do decarb with no transformer upgrade. Do what you need to do, but don't increase that, because once you increase the transformer, then the wire, then the substation, and it goes all the way up, right? So it gets massive, and so where do you stop, right? Everyone's going to want to stack all this peak load up, and so we can't do that. So we know we're going into this, arena where stuff's not going to all fit at 4 to 9 p.m. and we have to move it. Okay, next. This is a typical load shape in Washington State. The point of this slide is to show that one technology will deliver 17% energy savings and 20 to 40% peak reductions. This is, of course, heat pump water heating. Ecotope has been working on heat pump water heating for about 14 years. We've done about 100 designs. We've played around with different stuff. But this is really the argument that, efficiency is really still the game here. And and then you integrate kind of when you use it. And so the idea is, these are electric tanks in the units. These are central loops. And so just by doing, sort of this one technology jump, we get this huge benefit. And this is all going kind of in the right direction. Next. Okay, so now I'm going to jump into a couple of case studies, both current work and previous work. This is actually current work. This is tech company in San Jose. It starts with the C. They've got a large commercial kitchen. It handles the whole campus. This commercial kitchen is in the basement of this 4-story building. There's also a giant lab space inside of the building, 200,000 square foot building. The implementers bid out a like-for-like replacement on the gas. So let's go forward and I'll show you the problem first. Okay, so the problem is they want to decarb their hot water system. This is a massive load. It's 2,000 meals per hour commercial kitchen. What we did is, and that's what it looks like over there. So there's a 650 MBH boiler, 500 gallons of storage, sort of listed here. And the contractor initially did a like-for-like on this 650 and said, I want a heat pump water heater. Went to a contractor gave him $1 million bid. Client was like, no, get out of here. So then they came to us and said, can you help us? And we said, yeah, meter the building. So we metered the building. We found out what was actually going on, what the draw rate is, and then you go back and re-engineer it. So next slide. And so these are the results. 650 was what they had. And when we resized it, 170. So it's a factor of 4, right? So that's what's out there, is you go through and try to decarb all this gas, you're going to get the wrong answer. And so you actually have to kind of dig in. And then we said, okay, let's entertain load shift because PG&E is pretty expensive, 4 to 9. And so that became the number. But we're still a third less, and we're paying for a little more storage. I would pretty much guarantee that any gas boiler hot water system in a building is oversized. Probably about that same range. We see it all the time. It's just really conservative engineering, both at the mechanical and the electrical. And I think the electrical side is going to save us. David will test that. But anyway, so that I think is super big. This is also kind of highlighting Ecosizer 2.0, which is about to be released again, or re-released, an update. We've got some funding to do that, but that will allow custom load shapes. So you can put any building in, but you got to go get the metered data, hourly data, and then you can use it.
Is that software anybody can get?
Anyone. Yep. Ecosizer, you can just download Ecosizer. But yeah, that's the summary here. So 54 turns into 14 when you meter the kind of the hot water draws. We did 10 days, 1 hour metering. You establish an hourly rate, plug it into Ecosizer 2.0, which isn't out yet, and you can actually use the Ecosizer like you did, but you can do it custom.
For those who don't know, Ecosizer is a software for designing central heat pump water heaters that has lots of great buttons in it that Shawn led. And it's great that two's coming out.
Yeah, and thanks to Shawn, we got it funded.
Thanks to yourself. All I did is introduce you to a couple of people at the party.
That turns out that's all it takes. Okay, next. So this is the solution. So I'm digging in a little bit at the engineering level. Forgive me if it's too much, but I want to kind of explain a concept because I think this is also another thing to address is that it really is a design problem to try to decarb these buildings. And it isn't just hand it to a contractor and say, I want a heat pump water heater. Because you've got to put more into it. You've got to get specific on the spec is kind of our experience. This building was built with a gas boiler with no recirc. It's 200,000 square feet. It took 20 minutes or 15 minutes to get water all the way down to the kitchen. So 5 a.m. they go down there and turn all the taps on, prime the lines. So that was sort of problem one. And so they were thinking, oh, let's do this big loop. So anyway, there's a lot of complexity here, but the way that it's going to end up going is we've got storage on the roof, backup resistance with a heat pump, but there's also a heat recovery chiller in the plan too, because there's a giant server load. So there's all this waste heat coming off the heat recovery chiller. So we're going to preheat with the heat recovery chiller. We've got backup. Send the primary down to a bunch of A.O. Smiths in the kitchen, set up a recirc loop down there, and then you're sort of closer to the load, a lot less losses. So that's sort of one way to look at, you've got a big building, it doesn't have circ. I mean, that's pretty bad.
Are you heating the water up down in the kitchen that's getting rid of the priming problem, like not having the water there fast enough, but you're kind of reheating it? Like the water comes warm and then you heat it back up?
Yeah, oh, yeah, you'd sort of reheat this, but it's to get that there, but also to utilize the A.O. Smiths and get the cooling benefit in the kitchen.
Oh, because you're, yeah.
Yeah.
You guys all catch that? This is the heat pump that chills the kitchen.
Very good.
Yeah.
I've heard that for a heat pump water heater, the water input can't really be warm, like it
Yeah.
needs to be below some temperature, I don't know,
That's
like
true.
50 degrees. And it somehow it lowers the efficiency.
It absolutely does, yeah.
If the input water is at like say 70 or whatever.
Yeah.
So you're taking a penalty by preheating the water with the waste recovery.
Yeah, there might be a little bit of a penalty there. That's a really good point.
It's much
but-
better with CO2, it's much more an
Yeah.
issue than it is with more conventional refrigerants.
That's right. When you, like more conventional, exactly like Michael said, more conventional can handle up to 120 entering, but CO2 is sort of limited at about 85, 90. And then it really takes a dive. And that has to do with kind of the refrigerant cycle built inside. But CO2 is a different beast. But that's a
With the Air Smith, then it works pretty well
Yeah.
because it's conventional.
It is conventional, yeah. It's a 134A, and those are the 3-ton kind of newer models out. But the kitchen's really hot, and so this we hope will provide a dual benefit. So that's sort of one example of a way to address a big decarb load, but also solve the hot water wait time and the overheating in the kitchen. Kitchens are always hot. So, yeah.
What's the storage for on the, I mean, it's just to prime the water with this,
It's-
give it some heat before you?
It's so we can do load shift with the heat recovery chiller. And we're going to get that year round. And so, but this isn't going to go in till later. So we've got to have a system that works initially, but we're setting it up so that when that goes in, this is free. So, and then what we'll do there is pulse, that will essentially take care of, and we'll turn these off and just run off of those during peak. Okay, next. Second one, this is a project called Bayview Tower. This is in Seattle. It's a 100-unit, 14-story low-income housing project. And what we did is we developed a plug-and-play skid with a firm called Steffes. This is using the Mitsubishi CO2 heat pump water heater, and it's got storage inside. But we built this in a factory and shipped it out. It installed in 2 days. And so this was sort of addressing, we work a lot with NEA, BPA, but they're really after kind of a plug-and-play solution exactly for this. And so that's sort of, this was one solution here. We also designed this with load shift. And so we've been doing some tests on there, so I'll show you what we've been up to on that next. Okay, so this is our load shift, and I'm going to study this a little bit, but the data, there's a lot here, but I'll kind of show you what's going on. The axis over here is the hot water storage, and that's the red line. So you can see this is over a 24-hour day. These are our load shift periods, 4 to 9, and then the morning, 7 to 10 or 6 to 9, but somewhere in there. The storage is the red, and you can see what happens is during our load shift peaks, we're kind of drawing down the tanks. The green is the input to the heat pump. We turn it off completely for 4 hours, turn it back on. See, so we're buffering it up and we can kind of pull through. So we're doing this with the Mitsubishi. We had to write some code to kind of initiate changing the temperature. But in this load up period, we moved the temperature from 150 to 170. And we had to do that for capacity reason. But we tell the Mitsu to output full, and then we turn it off and let it coast through the peak. So we have this building right now running this way. We've got a time of use pilot. Energy is really cheap in Seattle. It's like 11 cents and 17 on this peak. So it's nothing like what we're dealing with here. So it's a much prettier scene in Seattle, I would say, with heat pump water heaters. But that is likely going to change. But these are experiments that were sponsored by Bonneville, and so we're continuing to kind of tweak this and this algorithm. But this logic has been written into the Mitsubishi product. And so if you go to Mitsubishi, what we're trying to do is someone says, I want load shift, and they just pull this up. So that's part of what we are trying to do is enable this technology. So we're working with all the major manufacturers to help them kind of get to this level. Because this is obviously where stuff's going. Okay. So this is a deep green retrofit of the Sitka Public Library up in Alaska. And this is in Southeast, which is the little stretch of land that kind of stretches down from the mainland Alaska. It's fairly mild climate. It's about 7,000 heating degree days. This was a cool little project. It's an 8,000 square foot library built, back in the 40s. At an EUI of 99, and so they brought us in, and so we did a bunch of upgrades, including Decarb. We did this in 2012. It's all electric, and I'll walk you through next some of the details. So the library turned out great. We took the EUI. So one of the big things that happens, we added 50% more area. So we had 8,000, and they wanted to expand, so we're now at 12,000. And so through the course of this, we went all in, deep green, so envelope, DOAS, heat pumps, and I'll show you some of that. We took the EUI from 99 to 32. So this is possible to do. It's straight, like attack the load, and then the HVAC budget, you're basically taking HVAC budget, putting it into conservation. It's the passive house classic argument. This was before Passive House, or maybe just was when it was getting started. But yeah, this project, I guess maybe go to the next one. And I'm going to dig in a little bit in the weeds. So some photos of how it works, but there's a VRF unit outside. This VRF transfers over to these heat exchangers, and those.
Variable refrigerant flow.
Variable refrigerant heat pump, variable refrigerant flow. And instead of routing the refrigerant all through the building, we converted to hot water and put it in the floor. And then we put the zones where the computer lab and the floor heat were on, and we put them together so you can dump the heat from the computer lab into the floor. And so you can do that anywhere, most libraries. But there's the radiant floor. There's that. There's also a really cool heat exchanger in this. It's called BPE. It's 5 feet long. It's a counterflow, but you get about 85% recovery. And the best fan energy you can buy, but you got to build it up. Anyway, we've used those there. They're pretty slick. There's a gorgeous view out there. Next. So I want to show some of the other tools that we use when we're looking at buildings. This is called a change point analysis. This comes out of the ASHRAE guideline, and this is called heating degree day regression analysis. But it's a really useful tool to look at bills. So we've developed a program that takes that methodology called TERM. You plug your bills in and you'll get these shapes. And these shapes are really telling about how your building's performing. And I'll walk you through it. So on the vertical is EUI, annualized EUI. On the horizontal is the outdoor temp, 55, 50, 45, 40. But change point is really about when it changes. And so the way it works is there's sort of 3 lines. The red is the electric post retrofit, so that's sort of the after. The green is the electric before, and the blue was the oil, so it's an oil-fired boiler. And as the temperature drops outside, your temperature-dependent bins or energy bins show up here, and it establishes a slope. And so when it is 35 degrees out, your space heating is using 90 EUI for that period. And so, but what's important is this slope is super important. This is a leaky building, and this is a high-performance building. The red is the after. So the base load was up here. This is the base electric, and this is the oil load. And then once we decarbed it, we turned into the red. So the red is now all electric. It's a much shallower slope. And so that's what we're after in all these high-performance buildings. This is like true load reduction. But we got the load down to about 900 square foot a ton. I don't know if that translates here, but it's essentially double, or it's half the HVAC of a normal building. And so there was the kind of the direct trade-off there. But this is really important. I've looked at hundreds of these, and so you can now, when you look at them, you see the slope, and you can say, oh yeah, there's no ERV on that, right? And so you can start to kind of. But it's a way to kind of really look into existing buildings and just figure out, like, okay, where are we at? How does it compare? Super useful tool. Next.
Shawn?
Yep.
you
Go back. Yeah.
So, was the original building the green plus the blue?
It was. Yeah.
And then the retrofitted building
Just the red. Yeah. So you'd have to add those up. Good point. So this would add up, and it's a little hard to kind of, yeah. So the base load EUI was 40. That's plugs and lights and fans. Fans were a big part of this. And now the new base load is down here, so we've reduced that. But keep in mind, we added 50% area. So I changed the variable. I added 50% of the area, so it's not actually apples to apples. It's actually lower. But yeah, that was the other part of this. This is just maybe some bragging, but here's Seattle libraries, so electric and their gas components. And then this is the Sitka after. So this was before, looks like most of the others. This is after. Yeah, and it's really, this is not rock, I mean, this is really simple stuff like ERVs, insulate well, turn stuff off that you don't need on, and then use good heat pumps. So we're looking at all of these buildings in Seattle right now, helping the city of Seattle kind of repeat that story. So yeah, but it's that's pretty significant, so we can do that.
Are you also seeing bill savings? Because just because you're saving
Yeah.
energy
Yeah.
doesn't mean you're necessarily reducing your bill. In some cases, you can save energy and actually
Absolutely,
decrease
that's a
your
really
bill.
good point. Significant savings, factor 2 on this because of the spread. In Sitka, they put in a new dam, Blue Lake Dam, and so they wanted to kind of use the power out of there, and they were using oil previously, and so oil is like $5 a gallon and 14 cents a kilowatt hour. So yeah, big savings here. So this was the one interesting part about this, and I'll show it maybe the next slide, is we had to do this without any transformer. And so what was on the table, they said, we're going to increase this, and here's the cost for the transformer. And I said, I want that money. And so we used it this way. And so it kind of showed like that's another way to kind of think a little bit forward on that. But when you're constrained by a transformer, yeah, you definitely want to think of that. But this is the pre-bills. We had a gap for construction, and this is the post. So again, you know, this is energy, not peak. So not to be confused, but you can see kind of the base load is about the same electric, and that's with increasing 50%. And so, but the story here is that there's fat in the lights budgets, there's fat in the transformer sizing. NEC is super conservative. David will tell you that. And I think most of the buildings, if you really attack the load, you can squeeze under the transformer in most of these retrofits. And that should be the criteria. That's my argument.
So you coming from like a cluster standpoint, like a nodes around those transformers? Obviously, it's not like one transformer.
It was
so
just.
You mean, but if you look at it from a building and or area, that's the way you should think about it. Like, how do you can squeeze in electrification in?
Yeah.
It's all a transformer upstream that it has to.
I mean, it was early in design, and so the electrical wants to do the loads, and we kind of hand them where we think we're going to be. And they look at it and say, oh, you keep this under here. And so you kind of work with that. But yeah. And so we kind of knew, they told us the KVA we got, and we just stayed under that. We kept pushing. So we ended up with 4-inch foam on the floor, triple glazing, 4-inch foam on the outside of the existing, 20, and then, 50 or 60 on the roof. So just classic super insulation.
And because it's commercial, they don't mind sharing that data with you, the utility.
No. I mean, yeah. I mean, we knew the size of it. I don't quite remember all the detail on it, but yeah, we knew the size, and the electrical is like, here's you guys stay under. And so that was the constraint.
So it sounds like you've effectively saved some serious money on infrastructure. I feel like we've run into on our projects for new construction, where we show this at new, showing, hey, look, we're staying under this transformer size, so let's just downsize the transformer. But our electrical engineers come back and say, yeah, but code requires that we use these values.
Right.
And therefore, I know that you're modeled to be this, but code's requiring that we make bigger assumptions and therefore buy the bigger gear. So have you had this issue? I think it's the National Electric Code was making this like this is a retrofit, so I guess it's not the same, it's already there, but any advice for new construction? Because if all the new buildings, this doesn't work for, because notwithstanding that that's what will happen in reality, you still needed to buy the big transformer,
Yeah.
then we're still with the big transformer.
Yeah, I'm gonna deflect that one over to David.
No. Rewrite the code.
I think that's the problem.
The power group that Jenny is leading is trying to rewrite the National Electrical Code
For
with
residential buildings.
Residential, yeah.
Single family right now, but if you want experience, I can connect you to that if you want to take that on, because it seems like it's a huge process, but yeah.
Come on over, the water's fine.
Do you ever consider drain water heat recovery?
Oh, we have, yeah. It's complicated to do in multifamily, but we have done a few of those. It's a kind of a small savings.
So sometimes it's cost effective to do so?
Yeah, I mean, we've stopped doing those because of the complexity in multifamily, because of the complexity of the riser. But yeah, I think it's like you're going to spend money, and we kind of just have always gravitated towards the heat pump water heater. It's better bang for the buck.
And I guess heat pump water heater this year, since it's so much more efficient, there's less savings that you can have.
Yeah. Oh, sorry, go ahead.
I wanted to make a follow-up comment on
Yeah.
the transformer side thing. So I think for just the building electrification, you can avoid the transformer upgrade, or you could even like not go as high as you need to go. But the question is EVs, like, if it's a public library, we now require new construction, and
Right.
there needs to be so many EV chargers at the site,
Right.
for parking and all that. And so if you add up all the EV load,
Yeah.
that definitely tips it over.
Yeah.
And that is the problem that we're looking to do.
So, if it's an existing building for the heat pump, stuff like that, there's that 220.87, right, for calculating the load. So that's what he was using. That's
Yeah.
what you can't use, right, because you have new buildings.
Okay.
For EVs, there's some interesting software that's out now that can limit that number. And so you could design to that.
The PowerFlex.
Yeah, like they're not the only one, but they're one of them. There's a company called Electrify that got acquired by Ford that does something pretty similar. So you could say, hey, it's limited to this number, right? And that's another way to do it, right? And just put limits on it.
Yeah, and this project didn't have any plug-in. It was a little early. Thanks, David. Next. All right, another one. This is the King County International Airport. It's in Seattle. This was a project. It's basically an admin and an airport kind of terminal for smaller jets. It's in Boeing Field. This had a really kind of old system called a multi-zone system, and it got replaced with Ventacity, DOAS, and VRF. And so this was just kind of going after that kind of the biggest bang for the buck, which is reduce the load with DOAS and then put in heat pumps. And so what happened is the EUI went from 155 to 46 just by doing that. And so they were massively over-ventilating with no heat recovery. And it was like you do that one measure really well, that's a huge reduction. And then the heat pump obviously helps. But that just kind of points out, like, we didn't go after the envelope. We didn't go after, the other parts. We just, that's all the funding we had. And we kind of got that bang. And then to get, further from 46 is where you start attacking the other, like the envelope and other stuff. But yeah, you get big savings with, moving to heat recovery ventilation systems and heat pumps.
Was it metered to know that was where the target was, or how did you know that?
Remember that term software? The slope was like this, and so you knew it. And then you go look at the design drawings, you're like, oh, it's massively over ventilated, and there's no one in there. the whole airport was just, they were trying to pressurize to keep the jet smells, which we ended up having to replace anyway, and we would just off balance the ERV in that zone, and so everything else was positive here, and made the concourse positive. But yeah, we basically looked at the bills, plugged them into our tool term, and we could see that slope, and that was like, okay, that's where it's at. And so you work to bring that slope down. Any other questions? Yep.
Does this fall, like, for all of the projects that you're renovating and you're putting in new equipment, how are the facility staff being trained to operate and maintain the new equipment? Because I know that transition is very interesting, because if you don't maintain it properly, then all your energy savings will be gone within 1 or 2 years.
This project was actually, the installer got the service contract, and so they're kind of doing most of that, and it's all DDC, and so there was a little bit of training at the DDC level, but we tried to match kind of what they had. Like if this room was zoned with a fan coil, we just replace it with a heat pump fan coil. So there was an effort there, but just after install, the contractors, this was an ESCO project, so it was a little more difficult, but they had a training piece there, and then that contractor has a service contract, so they kind of handle all the problems.
Is that what's happening in the other 3 sites that you were presenting on, like the library?
Yeah, bigger, like Sitka Library there's a staff in town, and they, it's a small little island, basically. It's not an island, but it's, a tiny little space. But it kind of depends on the building size and kind of what's going on. Obviously, bigger ones have these service contracts, but it tends to be most commercial projects are kind of handled by the service contractors. Not a lot of like in building. But multifamily is different. We get a lot. They have maintenance staff and that turn over a lot. Okay. Next. This is a fun project. So this is a new one that we're working on, and I'm going to bring Kanita in on. But this is up in Everett, Washington. But this is for the Everett Housing Authority, and we've been talking to them about some pretty big ideas. But what we want to try to do here, I'm just kind of showing this, maybe I'll come back in a few years, but 1,500 units of development over 12 buildings. And we are looking at trying to do essentially a GWP1 campus. So this is using CO2 heat pumps to do domestic hot water and space heat and do load shift and all of that. And so right now we're trying to gather funding to kind of do it on this first phase. But pretty exciting stuff, and they want to also talk about kind of a resiliency microgrid, and so that's a common theme up there. Solar on all the buildings, and then 100% EV coverage is the agenda there. So this is going to be really interesting to see these numbers. So
Level 2?
probably, I don't know.
When you say 100%, it's like every
Ev-
dwelling unit has one.
They have told us they want transformers for 100%, and so we're gonna kind of go in and figure out, how much with some load management software, what does that actually mean?
I think actually, like, our current reach mandate requires 100%.
Does it? Okay.
For all multifamily.
Wow. Yeah, we're not there in Washington yet, but we're probably a quarter.
We're not there in California, we're there in little cities, 2 places in the Bay Area.
Okay.
Is that a combination of level 1 and 2? Is that,
Okay.
In the end, if it's a big lot, it doesn't matter, right? Because it's more about, how many cars can you charge up over the course of a night? You run lots of level 1s all at the same time, or a few level 2s at a time, but it's how many kWh do you pump in the cars over the course of the night?
well, that's what I'm curious if they define what the requirement really is, because you could pump in just a little bit, and we're 100%. And that would be fine for most people, I think. I mean, I have thoughts on this too, but
Yeah.
I'm curious what is the requirement getting that granular to say you need umpteen kilowatts per vehicle? Or is it just saying charging?
No, it's KW per vehicle, it's all graphed, like there's a table of how much energy is allowed per code. It's definitely.
Specify the whole thing.
Yeah, cool.
Yeah, well, but I think there's an exception for, like, if you have load management software. There's something in there, I'm pretty sure.
Okay, got the last one here. So
Yes. Okay. a project Shawn knows well.
Oh, no. This is my first central heat pump, and it's just like, it's so shameful. Thank you for
No, it's not. It's not. It's a good story. I mean, it's just kind of show the evolution. Not a whole lot to say here, but just kind of right sizing is super important. So just trying to make the point. Next.
No.
Go back. Okay.
Tell the story.
I only have 5 minutes.
There was a terrible mechanical engineer who did not want to do a central heat pump in 2014.
Okay.
And he didn't know how, and he did exactly what he said don't do, which is made a gas boiler, turned it into a heat pump boiler, and did nothing else. And so every single component that you know better than I is broken in its own unique, horrible way. And they lived with like propane boilers up on the roof for years.
Right. Yeah. Yeah, it was kind of a bad scene, yeah. But it's good now. They're happy. Yes.
Thanks to Shawn.
This is a fun project here. This is water drop. So we designed this for a project in Menlo, and Small Planet kind of took it and took off with it. So, but it just got installed here. So this was installed in basically one day, craned up. These are designed to fit around, 50 or 100 people, kind of modules. And so there are 17 of these on 3 buildings down there, all kind of being installed now. So we're going to be metering those, and we'll kind of see them in action. But yeah, cool project. So this is a plug and play hot water plant. The whole thing is done and come out of the factory, you crane it up. So you can see there's 3 on a truck. These are heading down to the site, Menlo Park. And so we built pads on the roof, but you basically crane this thing up, put it in, and then you design smaller hot water loops around each one of them in a building so you can cut down on the recirc losses.
The refrigerant?
CO2, so there's Senko 2s, they're mounted on the back here. And so it's kind of designed to be modular. It's got like an engine and a caboose. Anyway, it was kind of a train. Anyway, so it's like that. But
and you can't mess them up. Most importantly,
right.
all these engineers out there can't screw it up because
this is what. Yeah. This is like one response to what we need: scale solutions. Solutions at scale. So take the old plant off and put it on it. So this is one option.
What's the bread and butter use of that? Where would you see that?
It's domestic hot water, and it's 100 people size load, or 50 or 100. So that's kind of the niche. So if you got 50 people to serve or 100, this is a great product. So like as a standalone for a smaller building, you're done. You put this thing on and you're done. Bigger building, you just kind of break it up into smaller pieces. So these are on 350 unit. Next. And that was the